Hello. So here are two of those problems worked out. Number 22, show that this is true for all positive integers n. And I regret showing this far. I kind of wanted to see if we can figure out the pattern here. The first term is 1 times 3. The second term is 2 times 4. The third term is 3 times 5. So the fourth term is going to be 4 times 6. But what is the pattern? First term, second term, third term. Well, the pattern is whatever term you're on, you're multiplying that integer. So the third term, you're starting with that integer, 3, multiplied by another integer. Well, by what? Well, in this case, 3's case, it's 5, which is 2 more than 3. And in this case, you're multiplying by 4, which is 2 more than 2. And 3 is 2 more than 1. So for any term, like the seventh term would be 7 times 9, the actual integer that the term represents times an integer 2 more places down. So that's why it is n times n plus 2. And if you add them all up, you get this. At least that's the claim, and we have to prove it. So it's very, very procedural. Step 1, show that it works for the first one when n is 1. Well, on the left-hand side of the equation, when n is 1, you get 3, 1 times 3. On the right side of the equation, you replace all these n's with 1, and you get 1 times 2 times 9 divided by 6, which is 18, divided by 6, which is 3. So it does work for the first term, but does it work for all of them? Step 2, you assume that it works up to some random positive integer k. So we're going to assume, we know it works for the first one. Step 2 is assuming that it works for some arbitrary amount. Step 3 is the heart of it, the key. You want to show that it works for the next one to k plus 1. And we're going to use the assumption to prove that it works for the k plus 1. And it looks like this, basically taking step 2 and replacing all those k values with k plus 1. So we start on the left side of the equal sign. Now this one involves some algebra at a higher level, not beyond your level, but at a higher level than other ones. Here you've got the left-hand side of the equation, and this first part, the first k amount, is equal to this. That's my assumption. So I'm going to, of course, replace this first part with this right here. But then now what? Keep in mind, you know where you're supposed to end. That's a big help. We want to end here. But how do I, follow the rules and lead this? This is not like you're not discovering something. We know what the end result is. We just have to show it. And notice the end result is one fraction. And at this point, you've got two fractions. So you should add them up, get a common denominator. So I'm going to multiply this by 6 over 6, and then combine like terms. Or, I'm sorry, just add up the two fractions. So now I've got one big fraction, and my result is one big fraction. But they're still not the same. I still got more work to do. How do I proceed? This is what you're focusing on. This is what we want to end up as. The denominator is all good. It's 6. But look at the numerator. It's k plus 1 times k plus 2 times this thing. And if you look at your numerator here, do you see that you've got a k plus 1 in the first term and a k plus 1 in the second term? You got two big terms here, this big guy plus this big guy. But both of those big terms have a k plus 1 in common. So I can treat that as a GCF and factor that out. And at this point, I don't know if that's the best way to do it, but I know that in the numerator, I've got two factors in the numerator. One is k plus 1, that's one factor, and the other factor is this big one. And I'm feeling good because I know I'm making headway. In this numerator, I've got three factors: k plus 1 times k plus 2 times this. So I think I'm making progress. Now I just need to get I need to understand this. And I've got two terms again, but there is no common factor that I can see. So how do you proceed? What should we do? I'm not sure what to do. So I know I can distribute this k and distribute this 6, and maybe that will help. So that's what I'm going to do. I mean, it's important. I wanted you to realize that I don't know how this is going to play out. I mean, maybe this is a dead end, but I know I can distribute this k, that's allowed, and I can distribute this 6, that's allowed. And I'm hoping that I can combine like terms and factor, and something will happen. Well, 7k and 6k are like terms, so they combine to become 13k. Now the question is, does this factor? And it does. It factors into 2k plus 9 times k plus 2. And I don't need these brackets anymore. The grouping doesn't matter anymore because everything is multiplication. And multiplication gets to be rearranged however I want it. So I'll just reverse these two factors to have the k plus 2 come first. Because remember, you want k plus 1 times k plus 2 times this. So now we're really, really close. How do I get this 2k? Let me show you the whole page. I hope you can see how close we are from this fraction to this fraction. And how do I get 2 times k plus 1 plus 7? How do I show that that's really the same thing as 2k plus 9? It's definitely easier to go up here and realize that if you distribute the 2, you get 2k plus 2, and then plus 7 gives you the 9. But it's worth practicing going in the other direction. You'll be a stronger algebra student for that. 2k plus 9. You know you want plus 7, so you can break up 9 into 2 plus 7, can't you? 2 plus 7 equals 9. And then I hope you notice that these first two terms, 2k and 2, both have a 2 in common, so you can factor that 2 out, leaving you with 2 times k plus 1 plus 7, and that is identical to what we wanted to show. So just like a lawyer defending her case to prove her client's innocence, that's exactly what we did. We knew the end result, but we started with the left side only, and we used algebra plus our assumption to show that it is true. So again, another way to put it is, as long as the previous one is true, then the next one is going to be true. That's what you just proved. That's mathematical induction in one sentence. If the previous one is true, then the next one is true. All right, and then this one, number 26, I'm not sure how to categorize this difficulty-wise, but we want to show that 2 is a factor of n squared plus 3n for every possible positive integer n. And let's just pick a random. I mean, I always did this in college to try to, it really helped me understand the problem. I mean, if you understand the problem, the solution should, in most cases, come pretty easily. I think the solution is 1% of the whole task. Understanding the problem is like 99% of it. So let's do a wild one. N is 917. Well, 917 squared plus 3 times 917 equals, definitely need my calculator for this, 917 squared plus 3 times 917 equals 843,640. And that is divisible by 2. I mean, I could divide it by 2 in my calculator, but this integer is ending in an even number, so it's divisible by 2. So it worked for some random term, the 917th term, but does it work for all? So we will prove it by mathematical induction. Step 1, show that it works for the first one. If n is 1, then you've got 1 squared plus 3 times 1, which is 4, and we all know that 4 is divisible by 2. So it does work for the first one and the 917th. Step 2, assume that it works for all of them up to a certain integer k. Step 3, show that it works for the next one, the k plus 1 term. So that means that replacing k squared plus 3k, replacing those two k values with k plus 1. So I get this. So now what makes this different and possibly more challenging is you have no equal sign. There's no equal sign. And you can see I've only got 4 steps here, which is far, far fewer steps than the previous one. So how can I show that this is actually divisible by 2? You have to use your assumption. So how am I going to get this to look like k squared plus 3k? And the only way I can see it, I mean, like the easiest way is to just simplify. I can take k plus 1 squared. K plus 1 times k plus 1. That's k squared plus 2k plus 1. And I could distribute that 3. That's 3k plus 3. And now you see you've got a k squared and you've got a plus 3k. But what justifies you rearranging this? And the justification is that addition is commutative. You can rearrange terms all you want, as long as you really just keep the sign in front of that term. So this is plus 3k. If you move this 3k anywhere, it better be plus 3k. So I'm going to move this plus 3k next to k squared. And then 1 plus 3, got 4. Now, I've only got one more. So how am I done in one step? Well, first of all, realize that look at it as two things that are being added. This plus this. Now, I already know from the assumption that this is divisible by 2. So the question is this divisible by 2? Because if I have one number that's divisible by 2 plus another number that's divisible by 2, then the whole thing is divisible by 2. So this is divisible by 2. I'm good there. But how can I prove that this is divisible by 2? And it's really just one step. They both have a 2 in common. You could factor out that 2. And this is divisible by 2. But how do I know? How do you know? Do you really know that this is divisible by 2? Remember, k represents an integer, a positive integer. It could even be negative, it doesn't matter, but a positive integer. If you take a positive integer and add 2, you will get another positive integer. And if you multiply that integer by 2, you're going to get an even number, guaranteed. And an even number, and all even numbers are divisible by 2. So this right here is guaranteed to be an even number because you're multiplying by 2. Any integer multiplied by 2 is even. So this is even based on our assumption. This is even because it has 2 as a factor. So an even number plus an even number is another even number, and all even numbers are divisible by 2. So that is the proof.